Okay, so we're starting on vectors today. Just going to go through some terms. You see here, vectors full chapter. The suggestion is if you print off this first page, you'll have a lot of the kind of important terms. Scalar vector, and then an indication of what a vector looks like or how we picture a vector. We picture it as an arrow. This is the back of the arrow, this is the front of the arrow, and that indicates that whatever is happening, it's going in this direction. And usually we make the arrow length relative to the size, quote unquote, of whatever's going on. So if I'm talking about a velocity, if I'm traveling 100 kilometers per hour in this direction, then I might make it a little bit shorter than if I'm doing 200 kilometers per hour in that section. We certainly can draw things to scale, 100 being half the size of 200, but for most of our purposes that won't be necessary. Still, getting some idea, getting things close is probably a good idea. So just, you can read through this. The tail of the vector is where things started. The head is where it ended. So essentially something has traveled from here to here, or in this case, the velocity again is representing sort of traveling that direction at a certain speed. Magnitude is always the size of the vector. So the word magnitude just means size. So if we're talking about, again, that 100 kilometers per hour north, essentially the size is the 100, the direction is the north. So vectors basically are things that have size and direction. And that's what this sort of set up here. Scalar, I skipped over it, but a scalar is just a quantity that has just a size. The temperature is 8 degrees. It's not 8 degrees towards the north or coming from the south, it's just 8 degrees. Volume is 3 liters of milk. It's not 3 liters of milk west. It's not 3 meters of milk to the right. Other things can have direction. I pushed the table forward. I drove my car south. These sorts of things. So there's the main difference. Scalar has no direction. Vector has direction. And then the last thing here is just kind of the idea of bearings. Bearings can be represented a couple of different ways. The first way is the true bearing, and this is where basically we just use an angle to represent the bearing. 0 is north, and then we turn clockwise to get to whatever it is we're looking at. So there's north is 0, here's 90, here's 180, and so 150 would be past the 90 and down to this point. We can also describe it as the quadrant bearing. And so again, we just want to be able to, we don't need to know the names, but we need to be able to represent or recognize, what each one is telling us. And so in the case of the quadrant bearing, it tells us something like start at the south, move 30 degrees towards the east. And so you can see that both of these are representing the same value. I start north and go 150 degrees around clockwise, or I start at the south and go 30 degrees to the east. I end up at the same point. Okay, so we flip back over here. Understanding vectors. So again, this is my interpretation of essentially the same things we just covered. Vectors have direction. Scalars, scalar value does not have direction. Quadrant bearing, compass readings, true bearings starting at 0, rotating clockwise. And opposite vectors, I'm not sure we didn't say it last time, but vectors of the same size, exactly the same size, but going in the opposite direction. And of course that makes sense. If I travel straight north for 200 kilometers and then I travel straight south for 200 kilometers, I end up right back where I was. So they're opposites, they cancel each other out. So just a couple of examples here. And again, you can sort of see that when you look at a scalar and a vector, the only difference is the direction. A scalar value of 20 kilometers per hour is just talking about the speed. 20 kilometers per hour towards the east is a vector value. It's a velocity. And again, the only difference is that I know the direction in this case. 60 feet versus 60 feet down, 20 kilograms versus 70 newtons. Okay, so just a quick little comment here. 70 newtons is an example of a force. I'm pushing forward, something like that. In the case of, and sort of says in the real world, we tend to think of our weight in terms of pounds or kilograms, but really that's a mass when we talk pounds and kilograms. So scientifically, weight should be in newtons. So essentially, instead of being, say, 180 pounds, I should be about 820 newtons. We don't tend to want to tell people those sorts of things, so we sort of stick with the pounds and the kilograms, and we assume that it's close enough for our purposes. The reason that works, of course, is because the force of gravity is the force that's acting on it. The direction is the pressure I'm putting down on the scale. And since that doesn't change, then we can just kind of adjust and say, well, my mass is basically what I can talk about. Note number 2, north 30 degrees west means to start at the north and go 30 degrees to the west. Okay, so we already sort of said that. And basically today's work will just be kind of using that terminology, understanding from the question what's being asked. They should be fairly easy questions, but as always, you ask questions of me as you need to. Thanks.